afternoon, and welcome to the Science Fiction to Science Fact event. My name is Kellee Campbell. I am the director at Flandrau Science Center and Planetarium at the University of Arizona. We are pleased to partner with the NASA Innovative Advanced Concept Program, also known as NIAC, to bring this event to you today. The University of Arizona has a long and proud history of working with NASA, beginning with the space race in the 1960s, when the first scientifically accurate maps of the moon were created right here at the U of A. And today, the University of Arizona leads NASA's OSIRIS-REx mission, which is a sample return mission to the near-Earth asteroid Bennu, which is scheduled to return samples in 2023. Here at Flandrau, we have the opportunity to share some of the exciting science and discoveries that have come from these missions and many others. Our interactive exhibits and planetarium shows explore our universe from Earth to space and everything in between, bringing science alive for visitors of all ages. Today, we are happy to host this virtual event with NIAC to share with you two exciting projects that are exploring cutting-edge science and pushing the limits of science and technology. During our time together today, you will hear presentations from two scientists who will be introduced in just a moment. After the presentations, we will reserve time for questions, and we encourage you to submit your questions at any time using the Q&A button at the bottom of your screen. We will certainly do our best to answer as many of your questions as possible, but please understand that we may not be able to get to all of them, considering we have many participants attending this event around the country. I'd like to thank all of you for joining us today, and I hope you enjoy the program. I'd now like to introduce you to Kathy Reilly. Kathy is the Strategic Partnerships Manager at the NIAC program, and she is also serving as our moderator today. At this time, Kathy, I'd like to turn it over to you.
Thank you very much, Kellee. And thank you to everyone at the Flandrau Science Center, mainly because we were supposed to have our symposium in Tucson itself, and this is an annual event for all of our researchers. And it became a virtual event, and we really wanted to connect with the audience, particularly in the Arizona area, but now we've been able to have a larger audience, so we're very happy to be here. So welcome to Science Fiction to Science Fact. Today, September 19th, we're in partnership with the Flandrau Science Center and Planetarium. I will introduce you to NIAC fellow, we call them fellows, they're our researchers, Saptarshi, Bandyopadhyay at NASA Jet Propulsion Laboratory, and NIAC fellow Douglas Willard. Doug is at the NASA Kennedy Space Center. I'd like to start with a short video.
5, 4, 3, 2, 1, ignition.
Okay, Houston, as I stand out here in the wonders of the unknown at Hadley, I sort of realize there's a fundamental truth to our nature. Man must explore.
I love my job. As the Strategic Partnerships at NASA headquarters for the NASA Innovative Advanced Concepts program, I get to bring space down to Earth on a regular basis. But I also get to work with amazing people, two of whom you'll meet today. I'm in charge of partnerships, communications, and outreach events like this. Right now we have a push to have a manned mission to the moon again as a proving ground for future missions. Missions to Mars. A small factoid, Mars was named by the ancient Romans for their god of war because of its reddish color was reminiscent of blood. In order to explore and for exploration to be successful, it needs technology. And the only way to produce tech is to attract the bright, creative minds that develop it and make it work. This is the Mars 2020 Perseverance rover. It will arrive on Jezero Crater on February 18th of 2021. So what is NIAC? NIAC develops early stage concepts, those that seem almost like science fiction, for NASA missions beyond the next generation. This is 10, 20, possibly 30 years out. It's extremely popular with the public. We're open to ideas not yet ready for prime time. Our projects are technically credible, including spin-off technologies to help humankind. Our studies relate to space travel, humans in space, materials, manufacturing, robotics, instruments, computing, and others. Basically, we're what's called an early stage program. So what does that mean? This is called the Space Technology Portfolio. NIAC is one of 13 programs within the Space Technology Mission Directorate at NASA headquarters in Washington, D.C. And each of these are our programs. We are the early stage innovation program on the far left. As things move from left to right on this slide, on the left is very early development, and on the far right are technology demonstrations. Those are flight ready. And it's called technology readiness level, and each one is, they sort of go up as you move across the screen. Most importantly, NIAC is not focused on one tech. It's advancing an incredible array of technologies. We're creating and enabling hundreds of studies. NIAC studies are propelling scientific discoveries, spurring incredible new technologies, powering new industries, and improving our lives in countless ways here on Earth. We fund researchers from many different institutions, universities, national labs, industry, small business, NASA centers, and individuals and garage inventors. We also inspire the next generation of scientists. These are students with Professor Bill Engblom at Embry-Riddle University with his study. This is his student team that he inspired. Not only at the college level, but also we're inspiring students to become the innovators of tomorrow at a younger age. This is an inspirational book series that we produced, each book about one of our researchers, that we produced in partnership with World Book Incorporated, which is in Chicago, for youth in grades 4 through 12. As a follow-up email, each of you will get a free ebook, access to the free ebooks, which are online at nasa.gov. This reaches students on a global level. And you're all invited to join us next week. If you want to get deep into tech, you can join us in our symposium, where we have all of our currently funded researchers are going to be showcasing their work and reporting on developments. It's a required meeting for them. It's on live stream, and you can go to this link at the bottom left and go to our symposium page and get on the live stream and register. It's free and open to the public, or you can just Google 2020 NIAC Symposium. Our team, the NIAC team, is an incredible group of people. And as a team, we try our best to nurture ingenuity. We try to foster innovation and to support our fellows' incredible creativity. Impossible. This is what our challenge is every day. We try our best to transform this simple 10-letter word, because together, we can make it possible. NIAC is the most open-ended and far-reaching of NASA's technology programs. It is open to anyone in the United States, and you're welcome to connect with me or anyone on the NIAC program regarding this. This is Captain Bruce McCandless in the background. He is jetpacking in orbit, and I put this slide in because his life is entirely dependent on the technology that's strapped to his back. So tech's important, especially in space. So now I'd like to introduce our two speakers for today. This is Saptarshi Bandyopadhyay from the NASA Jet Propulsion Laboratory. He has a 2020 NIAC Phase 1 study. It is a lunar crater radio telescope for the far side of the moon. Very exciting study, and something no one's ever thought of before. And we also will hear from Doug Willard from NASA Kennedy Space Center. Doug has a 2019 Phase 2 study, and it's called Solar Surfing. Very exciting. Both of the speakers for today know that creativity is seeing what everyone else has seen but thinking what no one else has thought. So I hope you enjoy today's talks, and I'd like to turn it over to our first presenter, Saptarshi. Thank you.
Thank you, Kathy. I hope you can both see me and hear me. Thank you, everyone, for this opportunity to talk about the Lunar Crater Radio Telescope on the far side of the moon. This project has been made possible thanks to an amazing team shown here. So let's dive deeper into this concept. So the picture on the right shows which wavelengths can be observed from Earth and which wavelengths are absorbed by the atmosphere while it reaches from outer space. So you can see the regions of 10-meter wavelengths or larger cannot really be observed from Earth because they are reflected by the ionosphere. And there's a lot of cool science that is out there, but because they're reflected by the ionosphere, even Earth orbiting satellites can't observe in that wavelength because the ionosphere causes a lot of noise. So we need to go somewhere far away to observe the universe in these wavelengths. Secondly, as I said, Earth creates a lot of noise. So we want to put a telescope in such a place that we can also hide from the Earth's noise. And that's why we selected to put a telescope on the far side of the moon. So Lunar Crater Radio Telescope, the idea is to put a telescope on the far side of the moon that will observe the wavelengths of 10 to 50 meter wavelengths. And we'll talk more about why that is interesting. But before that, let's look at the largest telescopes on Earth, the Arecibo telescope and the FAST telescope that are 300 meters and 500 meters in diameter each, respectively. And LCRT, if successful, would be a 1 kilometer telescope, which would be the largest field aperture telescope in the solar system. So the idea of building an Arecibo type telescope on the moon has been around for a long time, right from the 1950s when humans started thinking of going to the moon. Here is a picture from 1984 showing this concept. And what is interesting is that people have always been thinking of this idea, but have been hitting these roadblocks or technical challenges that have prevented this concept from ever taking off. So what we'll show you hopefully is that we now have the technology, or we think the feasibility of building the technology to put a telescope on the far side of the moon by addressing these technical challenges. They are selection of the lunar crater, then Arecibo type support structures like these things over here, which are very heavy. Then thermal strain, because temperature on the moon fluctuates from 100 degrees centigrade during the lunar day to minus 173 degrees centigrade during the night. And then transportation, if you have to build things in a crater, you have to basically go up and down a crater. And we're talking of huge craters here, like 3 to 5 kilometer size craters. So this is the concept that we are proposing to build. Clearly, we are still doing the feasibility study of this concept. In a large 3 to 5 kilometer diameter crater, we would deploy a 1 kilometer diameter mesh, and we would also suspend a receiver antenna over here. You'll see a lot of concept art in this presentation, and I would like to thank Vladimir for these pictures. Here is another view of the same telescope. You can see the cross-sectional view, and one of the things that immediately comes out is we don't need any of the large structural panels or cables that Arecibo needs, because our entire telescope is suspended inside a crater. So during this entire slideshow, I hope to convince you that we have figured a nice innovative solutions to solve those challenges that we talked of. So before that, what is it that we want to do? What is the science that we want to do with Arecibo? With LCRT. So here is a picture adapted from Professor Jack Burns' slide, who is a famous cosmologist, showing the recent Nobel Prizes in cosmology. You can see that we understand very well the region of the sky that Hubble has been looking at, and the region of the cosmic microwave background radiation that Kobe has been looking at. But there is no data over here in this region. That is really where LCRT wants to come in. So before that, this is obviously a famous picture of the Hubble Ultra Deep Field. And as you all might know, each of these small dots over here are essentially galaxies, very far, very early in our universe. On the other hand, this is the cosmic microwave background radiation that gives us a lot of information about the early universe. So I showed you two pictures from this region, the cosmic microwave and the Hubble Ultra Deep Field. So now let's try to understand why is there no data in this region, and why have we as humanity not really explored this region. So the first thing that we have to understand is during the dark ages, the universe was pretty simple. It had mainly hydrogen, photons, there might have been dark matter. We don't really understand that well. So if there is hydrogen, then we expect to see this 21 centimeter line. This is an interesting emission line that comes out of hydrogen when the spin of the electron flips and the hydrogen emits a 21 centimeter line. So 21 centimeter is like this big. And now there is this interesting concept in cosmology called cosmological redshift. But before that, let me explain Doppler redshift, which is something you all might know more easily. So the Doppler effect, in a sense. The idea is if you have a wavelength and it's moving away from you at a very fast speed, the wavelength increases, it becomes redder. So for example, these are the wavelengths of the sun. These are some of the absorption spectrums on the sun. And there's the same galaxy, same star that looks very similar to the sun, and it's moving away at a very fast velocity, 7% the speed of light. And you see it has all the absorption spectrums have moved to the right, towards the red. So it turns out the universe is also expanding, and this discovery was made around 1920s by Edwin Hubble, and that's why the Hubble telescope is named after him, at actually Mount Wilson Observatory, very close to JPL, and currently under a lot of threat from the forest fires. So what they observed was, what Hubble and his team observed was the universe itself was expanding. So these galaxies, which are very far away from us, are also moving away at a much higher velocity from us. So together, if you combine these two effects, the Doppler redshift or the cosmological redshift with the 21 centimeter line, turns out that same 21 centimeter line would be observed in the 10 meter to 50 meter wavelength band. So just think about it. The velocity of these galaxies is so large that a 21 centimeter line that is about this big would be like 10 meters in size. It's crazy to just think about it, but that's the universe we live in. So here is quite a complex picture, but I just want to point out that we expect, this is our best understanding of the theoretical models in this field, and we expect the signals to live in this region of the 10 meters to 50 meter wavelength. So that's what LCRT is going to observe, and that's why you need something far away, from Earth to observe in these wavelengths. So now the next set of questions, that was all the science. Now you would ask, okay, so what's technical challenges here? So let's go deeper. The first question was, can we find craters? Now turns out there is this mission, the Lunar Reconnaissance Orbiter mission, that has created very good 3-meter resolution maps of the moon. And we have found more than 82,000 craters in the 3 to 5 kilometer diameter. In fact, here are some cross-section profiles of these craters. And it looks like finding craters in this size, which have neat cross-section profiles, no peaks and outcrops, is quite easy. And here are some CAD models to show the LCRT mesh inside these craters. The next question was, okay, so what's that design? How do we get around the large Arecibo-like structures, which are very heavy? So here is an interesting idea. The idea here is we have a wire mesh, which is made out of just, large strings in a sense. And if you were to hold two ends of a string, they would take on a catenary shape. But a simple trick, which is to make the mass density vary as 1 by cos square theta, makes them take on a spherical shape. Now the advantage with that is because it's just thickness variation of the mesh, this thickness variation will be the same irrespective of what temperatures you expose it to. So from 100 degrees centigrade to minus 170 degrees centigrade, the mesh would just passively maintain its shape. Another idea is because it's a spherical shape, its focus is around half the radius below the center. So its focus, as you can see, is both the focus and the mesh are inside a crater. So we could just suspend this. And because moon has 1/6 the gravity of Earth, it's much easier to do this on the moon. And that's what we are essentially trying to create. Here are other ideas that we are using. Here's a design of the mesh. So turns out you would expect something on the moon to get hit by lots of micrometeorites and all. But because we are looking at 10 meters or larger wavelengths, there is a simple back of the envelope rule in electromagnetism that you need the mesh size to be at max lambda by 4. So we could have holes as big as 2.5 meters cos 2.5 meter, and the 10 meter wavelength would think it's a perfect reflecting stage. So that means we have a lot of free space in this mesh, which makes it very light. Here is another interesting design that makes it more micrometeorite resistant. So now let's discuss how do we plan to build this. We plan to travel in a single launch from Earth to Moon. And once it reaches near the crater, the spacecraft separates into two parts. One part lands on the crater rim, another part lands on the crater floor. And we will use these cool robots called duaxles that are being created in JPL for a number of lunar missions, and LCRT will also benefit from this effort. So the key idea of these robots is that they are capable of climbing down steep terrain like the cliff faces, because you would expect the cliff faces to be very, very steep and have lots of boulders and all. So here is some video showing the field test of this thing. So the idea would be that duaxle rovers would go in and actively pick up the wires and then deploy the entire system. So now let's discuss how do we plan to deploy LCRT. So the key deployment concepts are as follows. We'll divide it into 3 stages. The first stage is to deploy these guide and lift wires. The idea over here is before you deploy the actual mesh and the actual antenna, we want to deploy something so that we can then add tension to those wires. The second stage is to actually lift the antenna, the receiver antenna over here. And the third stage is to unfold the mesh over here. Now, I'm not showing you a large number of trade-off analysis and interesting concepts that we have come up with due to shortage of time, but I'll just show you one thing interesting, that the mesh is a huge 1 kilometer mesh that has to somehow live inside a small lander. So we'll use principles from origami to make this happen. Here is an example showing that you can have a large mesh and just pull along a few important directions and the entire thing will open up. And these are well understood principles in origami that we would invoke in our mesh. So the hope is at the end of this feasibility study, we could claim that yes, something like this LCRT is very much possible and feasible to build, and then understand what are the key technologies that need to be advanced so that we can make this mission a reality. So in summary, I have shown you a design of a large lunar crater radio telescope on the far side of the moon. It will observe the universe in the 10 to 50 meter radio wavelength band. And I've shown you why that is important, because there'll be large, it will give us a unique understanding of the evolution of the universe. There are many technical challenges that we spoke about that we are addressing. And I also want to add that, having the largest field aperture telescope in the solar system is already creating a lot of public excitement. When the NIAC award was announced, we were covered by a lot of media outlets, both nationally and internationally. There was also a lot of comparison to the Death Star, which I found very funny. So with this, I want to thank my LCRT team. There are a large number of both roboticists and scientists working in this team. And together, we are trying to make LCRT a reality. And thank you, and I'll be happy to take questions during this presentation. Thank you.
Thank you very much. We're going to take questions at the very end, if we can. If you want to put your questions in the Q&A at the bottom of the screen, that would be the best way, because after Doug talks, then we will go ahead and do that. Thank you very much, Saptarshi. You did a great job. I would like to introduce our second speaker for today, and that is Doug Willard from the NASA Kennedy Space Center. Doug?
Hi all. So my name is Doug Willard, and I put up this splash chart here to introduce myself and my team. This is our project is called Solar Surfing, and we're interested in getting as close as possible to the sun. And I included a picture of me as a young lad, and Kathy mentioned earlier about inspiring young folks. And I saw this picture and I thought, you know what? As I look back, I was just a normal kid, just a regular guy. And I think if there was one thing that made a difference between me going through school and going and pursuing the things that I pursued, and I'm really speaking to the people in the audience that are in the elementary school, junior high, and high school. And I want to just address those folks just briefly. The one thing that I had, and perhaps you guys have it as well, if I had to put my finger on it, would be curiosity. I was a curious kid. Sometimes drove people nuts. Might drive people crazy right now. I don't know. But that was the one thing that really took a hold of me, and I was really interested in things. And so at the end of this, our information is going to be made available. And if you have any questions about pursuing science or engineering, or how, you know, some tow-headed, that means a real blonde kid, came from a real small town to pursue trying to get near the sun, I would love to engage and let you know, at least tell you my story, or give you some guidance, or just talk. So with that said, I'll get into the pitch and back to solar surfing. So I'm interested in the sun. I'm a big fan of the sun, and one thing in particular, one of the big questions in science, or certainly heliophysics, which is the study of the sun, is it relates to something called the transition zone. And I put something on the right here, a little graph to give you an idea for those not familiar with the transition zone, what it is and why it might be interesting. And it's a graph and it's got some numbers on it, but I'm going to just decode it for you. On the left-hand side is the surface of the sun. We'll kind of call it the photosphere, but we'll just call it the surface of the sun. And as you go out from the surface of the sun, if you go to the right, the temperature starts out at about 6,000 Kelvin. It's pretty hot for you and me, or the oven, or something around town. But as you go out, a very small region is 10,000 kilometers. Only in 10,000 kilometers, the temperature goes up to over 1 million, which is a considerable jump in temperature in a relatively short region. And that's a transition zone. So not only does it go up, but it goes up as you go out further away from the sun, which might be counterintuitive. You might think, well, as you're closer to the sun, it's going to be hotter, but as you move away, it might get cooler. But you'll see that about this graph that's not the case. So that's an important question. And I also want to frame this talk is that I'm going to be using certain amounts of units, or certain units that you can get your head around. And I'm going to be talking about a solar radii, and I'll just turn here. So if you look at the picture on the right, the radius is from the center point all the way to the edge there. And so I'm going to be using that as a unit of measure to give you an idea. And the reason I do that, I could certainly talk about millions of kilometers and millions of miles, but I feel that you might get a better sense for how far things are in terms of numbers that you might be able to understand a little bit better. So to give you a sense, the Earth, on average, is about 214 solar radii. So if you took the center of the sun and you went out that radius 214 times, on average, that'd be about where we are. The Mercury is about 100 solar radii on average. And I put down here a couple of several different missions that we have sent spacecraft to the sun to understand a variety of things about the sun. And one of them I'll draw your attention particularly to, I'm a huge fan of, is Parker Solar Probe. I'm just an unapologetic fan of Parker Solar Probe. And in fact, the Parker is coming up on, I believe it's in 2 days. I believe it's on Monday, a little under 2 days from now. It's going to have another near approach. And we'll talk about that a little bit more. But to give you an idea, Parker Solar Probe will be the closest man-made spacecraft that's taking measurements by far. And so I'm going to use that as a jumping off place. And so the mission here is to get as close as possible. And my goal is to get to the transition zone. And just to give you a sense for where I'm going to start at, we're essentially through phase 1 of this. This is a phase 2. So our early work was pointed toward getting, how close could we get? Well, we feel pretty comfortable that we can get, and I say comfortable, air quotes around that, comfortable, still very hot, at 2 solar radii. So this is a very pictorial thing, kind of a cartoonish thing, and I've left out a lot of details, but the mission that we're talking about is going to use a very similar approach to the sun. It's actually not easy to get to the sun, and we're going to use we're going to orbit around the sun and around Venus, and get we're going to burn off angular momentum and get with each approach get ever closer and closer yet still, and that's one of the things that we're interested in. I should also mention that getting close to the sun or proximity to the sun has another application. There's people that are very interested in something called an Oberth maneuver, which is a maneuver that you would perform at with a spacecraft near a gravity well, or near, in this case, the biggest gravity object that we have in our solar system would be the sun. So the proximity of that, if you fired your motors, your rocket motors, at very, very particular time, you can actually assist yourself and gain more kinetic energy, or you can be moving faster out into deep space. So if you wanted to do deep space exploration, this particular technology, getting closer to the sun, would also be very beneficial. So the problem with getting close to the sun is it's so hot, and there's basically 2 strategies, or there's 2 different things at play here. One is to reflect the energy and not take it on, and the other way is to, in the case of Parker, they have some of that, but they use high temperature material, and it's usually has insulation behind it to withstand the energy coming off of the sun. And to reflect off the energy, you can have something called the selective surface. And currently, the current state of the art, for example, in the orbiter, this is the space shuttle, it has selective surfaces, meaning they try to reflect as much as possible. This current state of the art is, for at least if you consider that current state, is about 6%. So those are the 2 different things at play. This is a picture, not an actual picture of Parker at the sun, but this is a Parker Solar Probe, and you can see that the flat shield, which is facing the sun, that's a carbon composite, and there's carbon foam insulation behind it, and that's going to protect the spacecraft as it gets closer and closer to the sun, and that is what I consider to be the current state of the art. So that is one of the strategies. That's not the only strategy. In fact, I'm going to suggest a different one. So on the left of this is a cartoon which that's kind of the Parker approach, and you're going to have a shield out front, and it's going to be high temperature material, and it's going to be insulated with, relatively speaking, little backward infrared radiation going back to the payload, meaning you're going to protect the payload with that. Now, on the other approach, and this is the one that I'm suggesting, is to use the scattering, or actually not take on the energy initially, and but there's a price that you pay for that. One, you can only reflect back so much energy, and it turns out that the materials that reflect this energy aren't nearly as thermally they don't have the same ability to maintain their properties. They will melt and degrade, and they're not as able to handle the heat as the carbon composites are. So the idea is different, though. This is fundamentally different. So the idea is, instead of having insulation behind the shield, you actually wouldn't want to have insulation behind the shield, because that insulation would, in fact, make the shield hotter and make it worse. So what you would want to do, in fact, was let any energy that did make its way through the shield that didn't get reflected, you'd actually want it to go back as much as possible. And you'd say, well, that's no good because you're going to hit the payload. But relatively speaking, that would be a small amount of energy if you could scatter away as much as that sun's energy as possible. So to play on this a little bit further, the energy that would be sent back, if you painted this black, the back of the shield black, would be infrared, and you could use a secondary cone shield to handle that. It would be of an order that wouldn't hurt your payload. So that's the idea, that's the concept. And here's a little an idea of about how large that we're shooting for right now in some of our analysis. I'm just going to briefly cover some of the materials involved. There's a variety of materials that are involved, and many of these materials are, to give you a sense for what these kinds of materials are, a lot of these are materials that you might find in paint. So if you saw white paint, there's a very good possibility that some of the materials that are really good at scattering are found in paint. They're just the regular paint that you'd use at your house. And they are optimized to scatter back or reflect back light, and they're actually really good at that. But the downside about that paint is that the matrix, the stuff that makes it liquid and makes it not have mold on it and all the other things, unfortunately that absorbs way too much energy, so that wouldn't work. So what we've done is we've taken that raw material, only that material, and we're going to use a very specific diameter particle. This is, for those that are interested, about 200, 300 nanometer particles. And we're going to center that. And what center means is I'm going to push something together with heat in a very specific way so that we can change the spaces between the particles. It will turn out to be almost like a tile or a foam. And the thought is that that you need to control what's known as the mean free path, and that's when light goes in there and it's bouncing around. The distance between, on average, between different when it interacts with particles, that is going to be the mean free path. So if you can modulate that in such a way that you can enhance scattering. So that's the way that we could improve the scattering, in other words, reflecting. So this is a graph to give you an idea of barium fluoride. Our early work was on barium fluoride. We've now gone to yttrium oxide, which is another oxide that of several that we've used. And this graph shows on the right is the solar spectral. This is the irradiance from the sun. So this is the impact of the sun's energy. And then you see on the right is the barium fluoride. That's the red. And if you look across the bottom, you have the overlap of those two things, and that's measured in the units of wavelength. But the overlap is really far out to the right, and in fact, they don't overlap very much. And so the way that this works is, when you see the barium fluoride and it has that really flat spot, what that means is that it's not going to absorb the energy in those wavelengths. So it actually reflects. It's an excellent reflector of that particular energy from the sun. And then, so that's what we're going to use to our advantage. There's some other, I'm not going to go into details of this, but there's some other materials that you could use. But the point about this is, I'll just point at the barium fluoride. Barium fluoride's breakdown, that's where it's not nearly as thermally robust as like the carbon that we use on Parker Solar or on the bottom of the shuttle. But you're looking at about 900 degrees K. That's where it's going to start breaking down. Whereas yttrium isn't quite as good of a scatterer, but the benefit there is that you're not going to have nearly the amount of trouble, because you have another from 900 to 1200 roughly. So that's that. Also, one other thing to add: when you get this close to the sun, it actually becomes a geometry problem. This is not to scale. So as you get closer and closer to the sun, you have to make sure that the radiation doesn't, or the energy doesn't, that peak around the outside of your shield. And so you're going to have to make a shield that would be able to do that. So if you consider the sun on the left, I've exaggerated this in kind of the cartoon. It wouldn't look exactly like this, but hopefully this gives you the idea that there's going to have to be a curved shield, and that will be dependent on the distance from the sun. Flat surfaces work further away, but as you get close, you have to have curved. So the work that we're doing now is broken into two different categories. We have thermal analysis, and I'm not going to go into the nits of this thermal analysis, but in short, we have the red shield out front. That's the red part. That's the initial shield, and then the back of that's actually painted black. We want to transmit it as much as possible. So if we don't reflect it, we want to get it away from the yttrium as quickly as we can so it doesn't break down. And then there's a secondary shield that's at a 45 that is very reflective. And there's also a payload. So let's go on to this guy right here. And I'm just going to move on to some of the interesting other work that we have. So the idea here is that yttrium, as it turns out, is the best reflector that we have, that we're aware of. the yttrium actually reflects more than the standard. In other words, it has the ability to reflect more than spectralon. So if you go to NIST, then you say, well, what is 100% reflectance? You're going to say, okay, they're going to use spectralon or the repressed Teflon, I believe. This actually has a higher reflectance than spectralon. So it has an absorptivity it has a negative absorptivity. That's a relative number. And this gives you an idea of some of the material itself. This is some of our failures. These blobs were heated too much, and these are really close microscope photos of material that don't work. And then here's the material that does work. So this is a surface. This is 1,000 times your eye. And as you get closer and closer, you can see these 200 to 300 nanometer particles. And you could imagine there's a lot of surface area and a lot of opportunity for photons to bounce around in there. Likewise, as you cut through this inside the material, this is halfway through, so the cross section also has that same property. This is very important for the shield itself. So that's the empirical work the experimental work we're doing, and that informs our models. And if that is, I guess I'm gonna leave the questions for later. I guess we're gonna have questions all at the end.
Thank you very much, Doug. I appreciate it.
I hope I didn't go over there.
I think you would have been told by the team if you did.
Okay.
All right. Saptarshi, can you show your screen too? Because we're entering, so thank you both for coming. And again, thank you to the Planetarium and Science Center at Flandrau to, allow us to come in and talk about some interesting science. So we've got a lot of questions. So I'm going to start now and sort of read through a number of them. So before I do that, I did want the audience to get to know the two of you a little bit better. So I'm going to just put this out there. I need to know, for each of you, when you were younger, what you were like as a kid, which Doug talked on a little bit, but what was your aha moment? What was the thing that was it science fiction? Was it a movie? Was it someone you met or a science class? What allowed you to pursue the career that you're in now?
Maybe I could go ahead with that. So my name, Saptarshi, actually means the Big Dipper constellation. My parents chose it serendipitously, let's say. So at a very young age, I was doing astronomy, 3 years of age, trying to find all the constellations. Subsequently, I went into aerospace engineering because of how life worked out. And I really loved aerospace engineering. I bought to build some satellites, and since then I have had this hobby or love for astronomy, and my specialization is in aerospace engineering, and I've always been trying to combine those two. It's been a nice journey, and I'm pursuing many interesting projects that live on this intersection.
You're in a very interesting NASA center too, to
Yes.
learn, with a lot of cool collaborations. How about you, Doug?
I think the aha. I don't know if there was an aha moment. I was born this way. I don't know. That's not all. I'm sure. So I ask a lot of questions. I love to know things. I am inherently curious, and that has served me well. Curious and hard work will get you through a lot of stuff. If you're curious and you're willing to put the work in, you can go places. And if I had to put my finger on one thing, I can recall as a kid, and I do a lot of science. Science fair is my thing. I like to help kids with science fair. And the one thing that if I had to put my finger on would be rainbows. When I was a kid, rainbows, and frankly, to this day, rainbows are fascinating. They're fascinating. They're beautiful. They're compelling. They are interesting at all different levels of understanding, from when you're a kid to when you go through graduate school, or when you can understand them in many different ways. So I can recall as a kid in the kitchen, like many kids, and the window something hit and the rainbow was on the wall, and I was hooked. I was like, okay, that is the coolest thing I've ever seen. So I guess to answer your question, I would say when I was a kid in the kitchen with rainbow.
Thank you. Very cool. All right, well, let's go on to the questions. Let's see, Cameron Welsh has asked, Saptarshi, how will the LCRT be protected from asteroids? Saptarshi, you're on mute.
Yeah, so I could maybe share my screen and we can hopefully see it. So we have been worrying about micrometeorites. Now, if a large asteroid, like a kilometer-sized asteroid, comes towards LCRT, there's not much we can do. But micrometeorites are indeed a possibility because the moon does not have any atmosphere, so they won't just burn up in the atmosphere like they do on Earth. So there are a couple of ideas out here. Number one, the mesh itself is very hollow. So if most of it is empty space, because as I said, the mesh is made out of thin wires, and each of these holes over here is like 2.5 meter cross 2.5 meter, like much bigger than each human. So there's a lot of empty space. And even these wires can be built in this form. That is a wire with a crisscross shape. This is a patented design that exists. The idea here is that even if a micrometeorite takes out one of the sub wires, the entire wire itself doesn't fail. So these are two ideas in play right now. Yeah, thank you.
Okay. Is, again, Saptarshi, is variable mass in the mesh, is there a variable mass in the mesh to create a spherical shape?
Yes, that is indeed the idea. So if that's what we are trying to show with an experimental validation picture over here, that if you were to hold just a simple string, then it would take on a catenary shape, which is not a spherical shape. But with this mass density that you can calculate using simple calculus, it turns out that you get a spherical shape. In fact, I would recommend young kids to go and find what all other shapes you could get by just adding mass and strategic points on a string. It's a fun thing to do.
Very cool. This is a question for me. It wants to know how NIAC program, how it compares to DARPA, and if we ever collaborate with them. For those who don't know, DARPA is the Defense Advanced Research Projects Agency. It's the R&D agency for the Department of Defense. And NIAC does collaborate with DARPA. And that's it for me. Let me see. Jim Sidorchuk, for the LCRT, how would data be returned? Presumably it would also involve a satellite relay network.
Yep, I don't have a slide on that. So yes, there are many ideas out there. In fact, there is a lot of work being done because we expect the LUNAR gateway to come out sometime. So there's a lot of work being done on sending data from moon to Earth. So that's really not a very high risk technology anymore. Sending data from the far side can be done using relays, could be done using stationary satellites sitting near the L1, the Lagrangian point between Earth and moon, or on the other side of the moon. There's a lot of ideas out there.
Okay. Another one from Martin Randall. How would you control the Lunar Crater Telescope and get data back from it? I assume you would also need another lunar orbiter to serve as a relay station between the Earth and the far side of the moon.
Yeah, so we talked about the relay part of it, but controlling the telescope itself is actually an interesting feature that I didn't talk about. So maybe I'll just bring up a slide here. So what I want to show is this particular slide over here. So because a telescope is huge, it's a kilometer in size, it's very hard to move the telescope. So the other question is, given that we want to do science, the first question to ask is, do we want to move the telescope? And it turns out that moon itself is moving, right? So, and seeing different parts of the sky. So here is an example that shows what regions of the sky that moon would see if LCRT was at, say, 0 degree latitude, 20 degree latitude, 50 degree latitude, and you can see the strong galactic signal that we would like to stay away from. So essentially what I'm saying is we're possibly trying to put LCRT in the 20 degree north latitude such that as moon rotates, we'll just observe this region of the sky. And these lines show the arc that LCRT would trace. So we are basically taking advantage of the fact that we happen to be sitting on another spaceship called Moon.
Okay. This is an interesting question. We're getting a number of questions about when these are going to be missions, when these are going to fly. Again, I want to stress that these are early stage programs. You know, we're an early stage program. These are early stage studies. There is no mission yet, but if you, in a perfect world, if the stars aligned, I had to say that, when would your, you know, how long do you think it would take for something to be mature? Doug, I'll go with you first.
Okay, a mission to the sun. So the technology that I have is to get in close proximity to the sun. Let's be clear. So I would not be making the instrument to do the measurements. There's another. So the technology is to get close. That technology is currently being worked on right now to go into a small satellite. It's a CubeSat, and there is another team at Kennedy that is working with the university to produce that CubeSat. And so it is very early to say that it's going to be going to the sun. I have completely focused on the material and the CubeSat mission, to be honest with you. So I haven't really considered the length. This is, as Kathy mentioned, a very early, an early technology. The concept of going with a scatterer versus a carbon shield, which is very traditional, would be a very different thing. So you don't have to prove that out before you have a major mission to the sun. So I would think that I actually don't know how long Parker's took to get going. Saptarshi, do you happen to know? I know you're from JPL. How long it took from cradle to grave? Because this is an interesting question. I think people think that missions can happen in a year or two, but I'm guessing that Parker was probably a dozen years in the making.
To my knowledge, I happened to listen to a talk on Parker. The first papers on the Parker solar probe idea written by Parker himself were in the 1960s and 1970s.
Right.
And the real push to get the mission started, you know, writing all the proposals and getting it out, started in the 1990s. So it's 30 years is.
That's probably a good. So I would say that we're at least that amount of time away from a mission going to the sun. So what you see launched in 2018, I'm assuming that you mean when we are actually going to get to the sun. So in 2018 was the launch. That mission may have been planned for starting at 15 years. There was proposals for that before that. So it could be a couple of decades before. With that said, I don't know if you guys know what CubeSats are. I don't know if you can see my hands. I don't know if can you guys see my hands? So it's 10 centimeters by 10 centimeters by 10 centimeters. That's one U, where they call it a U. And so you can have a 3U, meaning 3 of those, or 6 of those. And so they're currently working on a very small CubeSat to take this technology and prove it out in low Earth orbit. So I don't know if that helps to answer your question.
Space is hard and it takes a long time. So it's hard to have a crystal ball and these things would go. But it needed to be addressed because I think, as you said, some people may think it's just a few years. It's decades.
Right. It took 2 years, 18 to now to get to the sun. You know,
So okay. In the case of LCRT, I would say that we actually did a study of if every proposal we wrote from now on, it would still take us a decade to even make it anywhere close to a flight mission. But that's not how science works. That's not how space research works at all. So I would be very surprised if by the time, or very positively surprised if by the time I retire, LCRT is a flight or is close to flight. That's how much time missions usually take. And the reason for that is very interesting. We are at the cutting edge of exploration. So, and exploration is hard. So there are many things that are out there that we do not know, that we will know, and we'll get stuck. And as we keep pushing the boundaries of knowledge, and we'll figure out those technologies, and then we'll be ready for launch. So So yeah, I would say anything like less than 20, 30 years is not going to happen.
Yeah. Okay. Question for you,
But
Doug.
yeah.
What would happen if you went into a stationary orbit above the sun?
Well, if you went into a stationary orbit, it would depend on how far you are away. So we could go. We could get. We do analysis. In fact, we've done analysis at 2 radii, which is known as a steady state. So you're taking only on the solar flux. At 2 radii, we have. As long as I got a picture, I'm going to show it. How about that? And I do want to show this at the very end, Kathy. I forgot to do that.
No problem. You can show it.
So this is the analysis for those out there like Thermal Desktop. This is Thermal Desktop. And so this is a steady state at 2 radii. We'll put your payload, which is the pointy end, at about 260K. So we won't be going into a circular orbit, but with 150 watt payload. So if you figure you're producing 150 watts in your instruments, and there's some other, for those that like spacecraft, you got gold Kapton, and it's got such emissivity, and there's a lot of things that go into this model. But at steady state, I can maintain a 260K, and that is with titanium struts, with titanium with this is notional, but typical struts that you might imagine, a reflective shield will get you to about 260K. For payloads that would be with an instrument suite that we would imagine that you would want to go in here, measure the magnetic field and the corona, that 260 should be sufficient. Now, the idea to get really close, however, and if you want to know more about this, I can get in more detail, but that's going to be at the symposium. The idea is that we would be in the hot zone, if you will, for about 90 minutes. I'm going to go back to here. So if you look at this picture, you're actually in the hot zone, meaning you're really close on your approach for only about 90 minutes. So really you're asking a steady state, meaning a constant orbit, but it's really a transient problem, which is much more difficult. And for those out there that care, it's also, it's not just temperature dependent, but it's also wavelength dependent, which makes the problem much more interesting. And by interesting, that's a euphemism for difficult.
Okay. Does the Parker use aerogels for insulation? People are interested in what it's using for insulation now.
So I didn't work on Parker, but I am very familiar with aerogel. We use it quite a bit at Kennedy. That's one of our main technologies down at Kennedy. To my knowledge, they did not. I believe that it's a carbon composite with carbon foam. So that wouldn't be, I don't know that it's exactly like, if you're familiar with the leading edge of the orbiter, the shuttle, which is a carbon-carbon composite, or the nose cone. Some people might be more familiar with that. But it is that type of material, a carbon composite that's going to be able to withstand tremendous temperatures, and then you put insulation in the form of carbon insulation behind that. I think you can kind of see here a picture of that. That's not an actual picture of it, but an artist's rendition of that. And I don't believe that they use aerogel.
Okay. All right. We're getting another group of questions. They want to know, what types of things will you hope to observe with the Lunar Radio Telescope? Some people may not understand what a radio telescope is. And another question related to that was, will you be looking at cosmic microwave background?
Okay, I'll just pull up the picture over here. So this is what we care about. This is a picture of our evolution, our understanding of the evolution of the universe. So this is Big Bang and this is present day at the bottom. And the idea here is LCRT, as you can see, will study these regions of the evolution, the dark ages, cosmic dawn, and reionization. You could potentially observe cosmic microwave background radiation. But because there are much better ways to do it using satellites, and there are significantly better technology out there, it's not really that much value for money, I would say. So this is the main essence of what we want to do. If you want to go deeper, I could go deeper, which is on a very different level because it's a science thing. So we want to, as I talked about, we want to look at the 21 centimeter line that has been highly redshifted because of cosmological redshift. So cosmological redshift is shown in Z over here. So approximately like 100 cosmological redshifts. So that's the signal from the dark ages that we'll pick up. And that signal, as opposed to cosmic microwave background radiation, which is just one signal at one single redshift, this is a continuum. So you get different slices of the universe, if you like you get to see multiple pictures, one in, an example would be one in, you take a picture of the same thing, but you put a red filter, you put a blue filter, you put a violet filter. Similarly, you can get multiple filters of the universe in that wavelength. And that's kind of what we are trying to measure using this.
Thank you, Saptarshi. Doug, what information are you trying to obtain? This is from Katherine Nettesheim, about the transition zone. And do those higher increasing temperatures away from the sun have implications for Earth?
So I can tell you that that what I believe is the cause of those higher temperatures is interactions with magnetic fields. I'm not an expert in that particular area. I'm an expert in getting close to that area, but I'm super interested in getting close. Does it have implications to Earth? Yes. So when you have these solar events that occur, we feel them on Earth, and if they're big enough, they can affect electronics and transportation and a variety of things in a very negative way. I was actually, I wasn't around in I believe in the 50s, but I was reading up on an event that occurred during that period of time, and it would have, if it would have occurred now, they measured the impact in U.S. dollars. I believe it was in the trillions of impacts that could occur because of a solar event that radiation would reach out to the Earth and really damage our infrastructure. It wouldn't simply be you'd have a bad phone call. It would be some serious implications. So yes, it could. Understanding that. Now, can you stop it? I don't know. I know that understanding, I'm inherently curious. I'm a scientist. I want to understand it. Right now, my interest is understanding the material that will get us there. But I do know that there are theories, there are ideas. But I also believe, as a physicist, that and a theorist, I might add. But until theories are fantastic, but until I actually see experimental evidence, at least myself, I'm not convinced. So taking actual direct measurements to me is very important. What are those measurements, and what is the suite of that is going to take those measurements of the magnetic field and the temperatures and the particles? I'm going to defer that to a registered heliophysicist. I'm a quantum mechanics condensed matter person.
Okay.
Sorry, Kathy.
Go ahead.
I wanted to be clear. I know how to get us there. I'm not the person that's going to take the measurements.
Yep. Again, for you, Doug, is any of the heat load conductive? Mirrors have 4 nines reflectivity. Why is this not used? Why not use mirrors?
Well, they reflect a lot of light. They also absorb a lot of energy. So if you're looking at only the visible, that's true. But if you look at the infrared, where the bulk of it's going to be, your mirror is going to melt pretty quickly. So that's why mirrors aren't used. Is it conductive? No, it's radiation. There is conductivity. I don't want to get too ahead. So there is conduction that goes from the shield along the struts to the secondary shield and the payload. But I assume that you're talking about is it conductive, like there's an atmosphere. There is particle impact. That is something else we're looking at. So the large particles and the degradation of the shield. I didn't really talk about that, but what will occur is there could be galactic very high energy particles that can impact the material, and it will degrade those, and eventually it will lose its thermal properties, and it will no longer be effective at scattering. That's what will happen. Okay. So that's another aspect of it. Yeah.
Okay. Doug, again for you, people are excited. Can you explain the difficulties in terms of getting the solar surface to the sun given the orbital velocity of Earth? Basically, the question is, it's not as easy as just aiming and launching and relying on the sun's gravity to take over, correct?
That is correct. So I actually avoided, just to avoid the orbital mechanics of how, so we used Parker Solar as our bogey. I mean, that's the way that we got there. I also thought I saw another question, do you have multiple passes? So I did a bad job of explaining that. So just like Parker, you have many passes that are getting closer and closer and closer with each pass. You're burning off angular momentum, and you're getting closer and closer. You actually, I think there's a couple of I don't say standard ways, but there's a couple of easy ways. I think you go around Jupiter and come back. It's an orbital mechanics question, but it is not as simple as you just point it to the sun and hope for the best. Now, you actually, it's very difficult to do. You have to essentially burn off as much angular momentum as you possibly can. And the ideal at the end of this, there is also ideas that we're considering of having essentially at the end, we could have a final burn and to go directly into the sun. So there will be several passes, perhaps dozens of passes, with ever, getting closer and closer and closer. The last of which being just to send the probe directly into the sun. That's another thought. I don't know if that, I don't think I answered that question.
Helpful.
Okay.
Yeah. Okay. Really intriguing, sort of a technical question from Carl Goodwin. This is for you, Saptarshi. A spacecraft at L1 does not help relay data from the Earth to the lunar far side. L2 or L4 or L5 would be useful, and L4 and 5 are theoretically able to stay on station without station keeping maneuvers. Just a statement.
Okay. I mean, when something is parked at L1, that doesn't exactly sit on L1. It moves around the L1 point. And when it moves around, that time you're actually not obstructed by the moon. You can look back at Earth. Because L1 is significantly farther away from the moon if you look at the actual scale. So the moon is actually pretty small when the spacecraft is on L1. And of course, another simple trick would be the spacecraft would communicate to a geostationary satellite, which is also significantly far away from Earth. And then the geostationary would communicate to Earth. Yeah.
Okay. Saptarshi, this is another one for you. They want to know, this is Melissa Cox. She wants to know, with the irregularities of the surface of the moon, does your concept need to be somewhat perfectly concave to get accurate data?
No, that's a very good question, and we are trying to understand it more. So the way the electromagnetics works of a mesh, if you had a perfect mesh, you could use a perfect equation to work out what is the gain pattern of this mesh and what is the sensitivity and what is the signal, how good the signal would be. But if there are small irregularities in the mesh, you could still work it out. Now you have to work it out numerically. So somehow what we need to do is to get a very good understanding of the mesh shape after it has been deployed. And we are figuring out how to do that. There are these ideas of indoor localization that exist on Earth. But it's actually a chicken and egg problem, because usually how you calibrate an antenna on Earth is you take it, show it a source, and you then what that source is supposed to look like for this antenna. That's how you know that, okay, this is how much is the deformation in the antenna. But we are going to be observing in wavelengths where we don't know anything about. So bringing a source in to actually calibrate the antenna would be hard. And we have ideas like we could send some orbiting orbiting CubeSats that would ping in, say, the 10-meter wavelength or the 15-meter wavelength, and then we could calibrate the antenna using that method. Those are, finer details. We are nowhere close to that. Yeah.
And then another sort of a telescope question for you, Saptarshi. Could synthetic aperture technology, for example, multiple smaller telescopes in space, could that be used to achieve similar or greater results versus a lunar telescope?
Yeah, I didn't talk more about it, but there are a number of such ideas out here. So for example, there's the synthetic aperture is more of an optical world, and in the radio world, it's similar to sparse dipole array. That's the word that's used, which kind of all work in the same basic science of interferometry. So this mission called FarSide is really right now the leading candidate to possibly go up into space. There are also these ideas using this sparse dipole array to put constellations of satellites on the far side, and ALPHA and DARE and ALPHA. These are some missions that are trying to push this concept. So there are a number of other mission concepts also trying to do the same thing using other techniques.
Very nice. Thank you. Doug, we're getting more and more questions wanting to know, what does the payload potentially consist of for your study? I know that you're trying to get us there, but obviously you have been in discussions with what the payload may be.
Right. So we had instruments that were nominally based on the avionics, and the instruments that were on Parker. That was what we based it on, simply because it was it gave us the what we really needed was volume and the power, so power dissipation, because that dictates the thermal environment, which our technology is the thermal management system. That is the technology, the materials. So if you're asking, it would be magnetic field measurements. I am not well versed in the instruments. I have to say that I'm not. I hope that I didn't oversell this. I'm not a heliophysicist. I know a lot about materials and light and energy. So that's where I get to my knowledge, it would be the similar suite of not exactly the same suite of instruments as Parker. The difference is, just to give you an idea, Parker's going to get 8.8, which is incredibly impressive. I'm a huge fan of Parker. There's a marked difference between 8.8 and 1. So at the actual getting to the sun is no small feat. That's kind of the big deal. I could also, I don't know, it's also made clear the idea of, somebody was asking about, I was going through the comments about reflections, and I actually misspelled the word. Thank you for whoever pointed that out. But some of you may have seen in the slides that it had that might have been confusing. I think maybe based on the comments, I could have confused some folks, and that is here, the absorptance. The absorptance is a negative value. So those that are familiar with absorptance, or perhaps the complement to that would be the reflectance. This corresponds, a negative value of absorptance actually corresponds to over 100% reflectance, which is might mess you up, because you're thinking, well, how could something reflect more than 100%? This is like some sort of, it's breaking the second law, right? Thermodynamics, excuse me. No, so that's based on a standard. So if you go to the NIST standard, so that's a relative measurement. So those that might have seen that and said, wait a minute, you can't have a negative absorbance. That's not strictly true. That's not strictly true. So you're just saying that you have a better absorbance than the NIST standard is all. Okay. So I hope I didn't confuse the issue. And it can be confusing because it's weird. Why would you have negative? That seems odd.
Absolutely. From someone named Guy in the chat for Saptarshi. He wants to know about, being a fixed telescope, how limited is the field of view? It wouldn't be 100%, correct?
No, it's not. It's only that thin sliver in the sky that we'll observe. But since we are interested in what happens in the early universe, that thin sliver of the sky is a good enough approximation of the entire sky. And there's also another question I saw about why do we care about the early universe? Now, the reason why we care is, if I may share this slide that is kind of, so I'm not going to talk about something that is not my field of expertise at all. I do not understand the high physics that goes into this, but I have, as I come to understand, all our normal matter is barely like 4 to 5% of the universe as we know it today. There is some large 21% of it is dark matter and 74% of it is dark energy. I can't tell you more than these words because that's not my field of expertise. But what I can say is observing the early universe gives us a window into these two quantities. And that's why we want to observe it. So just look around you. Everything that you see is just 4% of this universe. Like there could be dark matter and dark energy around you and we would not know because we just don't know anything about it. So it actually matters. It's just that we don't realize it, so we don't care, but it's out there, it's around us.
Thank you. There are other questions about aerogels and how hot it has to be for them to burn, but I don't know if you two are experts on aerogels, but apparently they're intriguing to people. So any kind of information you can give us would be helpful.
I wish that I sit right next to one of the world's experts in aerogels, as a matter of fact. I know what they are. I've seen them. They're impressive. I don't know the temperature that they burn at, I have to say. I tell you what I could do. If there's a chat here, I can text my buddy and find out when they burn up. I don't even know if he knows when they burn up. That's not a test that I don't think we would typically do on aerogel, but it could be. I assume that you're asking when it melts or when it thermally degrades.
That's what it seems like, yeah.
Yeah.
Okay. There was a question to me about giving an example of a NIAC innovation that went through the technology phases and ultimately was developed and used in a NASA project. The best example currently, again, NIAC has been within the NASA headquarters for only 10 years, and most missions take 20 to 30 years. So we're still early, we're that early stage, but we do have Chris Walker at the University of Arizona, who started with a balloon study, and that has transformed into a company called Freefall Aerospace that is currently developing, basically helping with the 5G revolution. And he has a student-led CatSat mission, it's called, that should be going out. And he will be at our symposium, so you can ask him there if you'd like through live stream. Let's see what other questions we have here. The question about solar flares, are those going to impact you, Doug?
Yes. So this I do know. So if there's a solar flare, what will happen is we'll get fried. There is no way around it. Thermally, there is not a lot you're going to be able to do with materials. I don't care how good of a scatterer you have, you will burn up. And I've been asked that several times. But what if there's a big flare? Well, then it's a bad day. I don't have a technology that can withstand a solar flare.
Yeah, there's a big wow.
Yeah,
There's a big wow.
Sorry. Right. Yeah, as Saptarshi mentioned, these are leading technologies. I mean, just simply to be able to have something that has an absorbance, a negative absorbance, is somewhat astonishing. I really, and Kathy knows this, I've shared this before. If you see this material, I believe it's called the dynamic, the video that I showed does not do it justice. If you see the material and you see how much it reflects, as it scatters, and you can see also how much it does not take on an energy across the spectrum, it's startling. And the video just does not do it justice. So I don't have, unfortunately, a way to prevent us getting fried from a solar flare. That will overwhelm us.
Yeah.
So this is space is a risky business. That's all I can tell you.
Days has asked, at 2 solar radii, Is there meaningful pressure load on the structure?
No.
Okay. Okay, good.
No. So are we going to look at it? Yes, and we're going to do a full structural analysis, and we're going to look at that as we get closer and closer. But as of right now, the answer is no.
Okay. Saptarshi, those things that are being developed at JPL, is there concern about the terrain when they start pulling apart and putting the mesh out? They're thinking to how previous rovers at Mars have gotten stuck in terrain.
Yeah, so that's a very good question. That's why we have lots of different ideas that we are looking at. There is a lot of concern about what terrain we would be on and what kind of deployment we would like to see on those terrain. So just to show you some ideas that we've looked at, we could deploy, while coming down into the crater, or we could deploy after we reach the crater, we go out. So here is a concept art showing how we would deploy such a telescope. This antenna structure has a very interesting property that while you're pulling on these wires, this crater rim would kind of rub on the wire, and then that could basically tear apart the wire, because Moon has not really seen erosion. So all the small dust over there is very fine, but very angular and very, very abrasive. In fact, that's one of the big lessons that we learned from almost all Moon missions, is that robotic instruments break down very fast because this really fine lunar dust enters into motor circuits, into all sorts of moving gears, everything, and just drags them. So we have to figure out how to put pulleys over there to somehow avoid this dragging on the surface. A lot of things. We are extremely lucky. We have 3-meter resolution maps, so we can genuinely actually look and see if there are 3-meter large boulders that we would like to avoid. But below that, we have to have quite a lot of design challenges that exist in this deployment area.
Okay. There was a question about, at the very beginning of your talk, Saptarshi, you were talking about temperature swings on the Moon. Yeah. There's an anonymous person who wants to know, how was that addressed?
So the key idea is simple. Our entire thing is passively shaped, so we don't really have to worry about temperature swings, because as something changes temperature uniformly across the surface, we can just, the entire thing would change shape as one whole unit. So what I'm trying to say is this mesh would just change its shape, but would increase or reduce in size because of temperature, but its shape won't change because the shape is passively maintained by this thickness variation. So that's kind of an innovation that is driving the underlying design.
Okay. A number of people are asking questions about, do you just go once and you bring everything with you, or are there multiple missions to basically allow Saptarshi, your study to come to life? So
right now we are trying to do everything in one mission. It would be just one launch and land on the far side, but the lander itself would break into 2 parts. So because that's what the idea of this NIAC study is, that we understand the feasibility of this concept. As of now, it looks like we can still manage to put everything into a large rocket. I don't want to define the word large here because many rockets have many different propellant or payload carrying capacities. But maybe by the end of this year, we should have an answer to this question. But as of now, we're looking at just one launch.
Okay. Also, someone wants to know about moon dust. Could the buildup possibly be a problem?
Yeah, moon dust is a problem. It's many of the rovers, even the Chinese rover and a bunch of other are US made, and other robots have not worked on or have died later on the moon because of the buildup or moon dust entering into the rotating parts. As you might have realized from our design, everything is passive. So once the telescope is built, we don't move anything. That's kind of one of the main drivers why we don't want to move anything, because we don't think things will survive for long. But the second thing is moon dust is very small. So it doesn't really affect the radio reflection properties of the mesh or the receiver or anything. There's an interesting thing that we really don't understand about moon dust is, as the sun goes above the lunar surface, supposedly the dust comes up and makes a nice fog or a haze. We don't really understand what it does. We don't know how it will affect, but these are open questions out there that we would like to answer.
Okay. There's a question from Jack McLeod. This is more for me. He says, I know the concept was displayed earlier, but what is the realistic viability of a solar sail, and can one gain enough momentum to be of significance in space travel and exploration? Jack, you need to come to our symposium next week because we have someone talking about solar sails, a very innovative device. So in the email that's sent to you afterwards, you'll have to click on the live stream link and look for Grover Swartzlander. And I think, let's see, from Dan Hallett, DSLR camera sensors utilize a small vibration to clear dust. Similar idea for the wires, small vibrations intermittently. Would that work?
Yeah, maybe.
Yep.
We should look into it.
Okay. I think we are, I think 5:30. We were supposed to be ending, or at least on East Coast time. I'd like to thank both of you for a fantastic, very engaging day and lots of talk. And I'd like to thank the Flandrau team for putting this together and to getting a huge audience. We're so thankful. Are there any final words either one of you have?
I have one. Now we forgot twice. I didn't do this before, but I will point at the end of the pitch, and this will go out in an email at the end of this. For those that are interested or happen to enjoy a particular genre of art, there is a poster, 2-foot by 3-foot poster that's available for solar surfing at this website, and I think that Kathy is going to send that along with some other information about the upcoming NIAC symposium this coming week out in an email, right?
Yep, the Flandrau team will be sending it. I'll be sending it to them, and they'll be sending it to everybody who registered.
Got it. Okay.
And I'm going to pass this along to Kellee.
All right. Well, thank you all so much, Doug and Saptarshi. This was fascinating, and I'm sure that everybody else is excited as I am and inspired, not only by the science and the technology that you guys are pushing the limits with, but also your personal stories. There were a lot of people in the chat that could relate to your stories and how you became interested. So we really appreciate you spending the time with us and sharing your passion. Thank you all very much.
Thank you.
Bye-bye.
Goodbye.
Thank you, Kellee.